Welcome to the Rapid Cassandra e-learning course. We want you to quickly grasp the basics so that you can start building an application with Cassandra. This is the very first video, and you'll have an overview of the whole course. We're going to look at the course structure and the prerequisites that help you get the most out of the course. As we'll have hands-on examples in the later sections, the recommended configuration of the test environment will be introduced as well. This course is divided into 4 sections. Section 1, Building the Foundation, gives a high-level introduction of Cassandra. We'll look at the overview of the course that we'll be watching now. Then we'll look at Cassandra's high-level architecture and some of its important concepts. Data modeling is the most important thing in using Cassandra, and it makes Cassandra different from others. The unique features provided by its data model are supplemented to finish Section 1. Next, we'll learn how to design a data model. We'll use Cassandra query language to design and manipulate a data model. As Cassandra is a non-relational database, we'll use a different approach, called modeling by query, to design and evolve the data model, which is rather counterintuitive to those familiar with relational databases, such as MySQL and so on. It'll be explained in detail and followed by another crucial topic, indexing. The first 2 sections give us just enough theories to develop a running application. Section 3 details the steps of developing a Java application called Cassandra Trader, which is a stock quote application and collects stock quote data from the free Yahoo Finance website and stores them into Cassandra for different kinds of technical analysis. Although Cassandra can be used in many programming languages, we'll use Java language to develop Cassandra Trader, and we will need a driver to connect Java to Cassandra. Also, we'll quickly install and prepare the sandbox. Then, we'll apply the modeling by query techniques to design the data model in CQL. When the design is finished, it's time to write the Java code to implement it. Then we'll write test cases to verify and validate the application to complete this section. In Section 4, we'll turn to the considerations and techniques of how to deploy Cassandra Trader into real-world production use. For example, we'll choose an appropriate replication strategy to scale out Cassandra and make minor changes to Cassandra Trader correspondingly. Monitoring is another important component of the production system. Cassandra provides a bunch of monitoring utilities and tools that we will introduce. Furthermore, we'll come across performance issues in some cases. We'll look at the tools provided by Cassandra to help us troubleshoot and tackle those issues. It's possible that a production system needs to respond to business changes. Cassandra's flexible data model comes to the rescue. We'll see how to roll out changes in a production environment. Finally, the last section of this course. A few prerequisites are nice to have to get the most out of the course. We'll primarily use Linux as the operating system, but Ubuntu is the preferred one. Knowing how to write simple shell script is highly beneficial. The installation and administration of Cassandra are assumed to be done and won't be covered in this course. Also, this course is for Cassandra 2.0 or above. For writing Cassandra Trader, we'll use JDK Standard Edition version 7. A basic knowledge of this is a definite advantage. We'll use Eclipse IDE to develop Cassandra Trader, so some knowledge about this will allow us to write programs even faster. We'll use Maven to manage the Spaghetti Java package dependencies and automate the unit tests. If you don't have all these prerequisites, don't panic. They'll be explained briefly. Now, switch the screen to My Development Environment. In the terminal, type CQLSH. So, the Cassandra installed on this machine is 2.0.9. If you've never installed Cassandra, you need to follow the steps in the link shown here to do so. Exit CQLSH. Then type NodeTool status, a single node cluster. Right. Type uname A. Ubuntu Linux 14.04, 64-bit with the kernel version as shown. Then type vmstat. The machine has a 4 GB memory. In summary, we understood the course structure and how it moves. We also listed out the preferred knowledge and skills to understand the course most effectively. Finally, the configuration of the development environment was introduced. Next, there will be a quick tour of Cassandra's architecture in 5 minutes. Welcome to Section 1 of the Rapid Cassandra course. Although we may be familiar with Cassandra, it's good to revise the key concepts here. We'll have a general view of the NoSQL databases, essences of Cassandra's architecture, and the key features. First, let's look at the background of why Cassandra was born. A very hot topic nowadays is big data, which is a result of the crazy amount of user-generated and machine-generated data. The generated data is not only gigantic in volume and fast in velocity, but also diversified in variety. Big data imposes new challenges to the traditional ways of handling data using relational databases, as they weren't designed for web scale. So a new breed of data management products was born, collectively called NoSQL. NoSQL is a short form of Not Only SQL, meaning that it's different from the relational databases. From 451 Research Group, around 100 databases are not relational, as shown in the light blue and light green regions, and one of the most popular NoSQL databases is Cassandra. Cassandra was born at Facebook and has been donated to Apache Software Foundation as an open-source project. It aims to store and manage very large amounts of structured data running on top of an infrastructure of hundreds or even thousands of nodes in multiple geographic areas, while providing linear scalability and superior reliability. Its architecture is based on Dynamo and Bigtable, inheriting the strengths from the two best-of-breed NoSQL databases. Dynamo is a proprietary, peer-to-peer, highly available key-value store developed by Amazon. It replicates data across nodes in the cluster to tolerate node failure and advocates the concept of eventual consistency. Its mechanism is explained in a published paper called Dynamo, Amazon's highly available key-value store. Bigtable is Google's core technology, addressing data persistence and management on web scale, providing superb read-write performance, linear scalability, and continuous availability. A paper called Bigtable, a distributed storage system for structured data, is freely available on the internet. Cassandra designs its distribution model with reference to Dynamo and its storage model to Bigtable. So it runs on a peer-to-peer architecture, and it's a column-oriented store and provides great schemaless flexibility to application developers. Cassandra also borrows the commit log mechanism from Bigtable to ensure data durability. Inherited from Dynamo, the ability to scale horizontally and incrementally is a key design feature. Cassandra dynamically partitions the data over the nodes in the cluster to achieve it. It attains high availability by replicating data at a number of nodes, which is configured by the so-called replication strategy. Replication strategy determines which nodes the replicas are placed. When a write occurs, the data will be immediately appended to the commit log on disk to ensure durability. Then Cassandra stores the data in an in-memory store called memtable to keep the hot and fresh data. When memtable is full, its content will be flushed to SSTable using sequential I/O, and the commit log is purged after the flush. As random I/O is avoided, write performance can be very high. On the flip side, when a read request occurs, the data to be returned is merged from all related SSTables and memtable. Timestamps are used to determine which one is up to date. The merged value is also stored in a write-through row cache to improve future read performance. Cassandra provides various tunable consistency levels for read and write operations. Consistency level is either the number of replicas that acknowledge a successful write in write operations, or the number of replicas contacted for a successful and consistent read operation. Cassandra also provides 3 repair mechanisms to tolerate failures. Read repair and hinted handoff are done by Cassandra internally and automatically. Anti-entropy is run by administrators manually. You may refer to the link shown here for a more detailed description of Cassandra's architecture. Here, Planet Cassandra summarizes the great features of Cassandra: elastic scalability, always-on architecture, and easy data distribution by appropriate replication strategies. Fast, linear scale performance by log-based sequential I/O read-write request handling mechanism. Flexible data storage by its both row and column-oriented storage model. Operational simplicity by its peer-to-peer architecture. Transactional support by its tunable eventual consistency. We reviewed the evolution of NoSQL databases as an alternative to deal with big data. Cassandra, being one of the NoSQL databases, provides an elegant architecture as a combination of the strengths of Amazon's Dynamo and Google's Bigtable. We also learned the great features provided by Cassandra. Next, we'll look at the unique Cassandra data model. Welcome to Building the Foundation. Cassandra's data model is pretty unique. A high-level understanding will allow us to correctly implement a data model. We'll look at Cassandra's storage model and its logical building blocks. Also, the important differences between Cassandra and a relational database will be introduced, particularly valuable for relational developers to migrate to Cassandra. We learned that Cassandra's storage model is a column-oriented store. A column-oriented store is basically a multidimensional map. It's a data structure resembling a map of a sorted map with a key. Map gives efficient key lookup, and the sorted nature provides efficient scans. Row key is a unique key and can hold a value. The inner sorted map allows a variable number of column keys. Both row key and column key can be strings, or any kind of byte arrays. Also, column key is stored in each column. Though it wastes storage space somehow to repeatedly store column key, it brings us a very powerful feature. That is, row key and column key can store data themselves, not just in column value. It's a trick that Cassandra uses to be schemaless, and allows the data model to be evolved organically over time. We'll revisit this in other videos. Cassandra's data model is composed of a few logical building blocks, and each of them is introduced bottom-up as follows. Column is the smallest data model element and storage unit. Don't be confused. Though it also exists in a relational database, it's a different thing in Cassandra. A column is a name-value pair plus a timestamp and an optional time-to-live value. The name and the value are byte arrays, corresponding to column key and column value in the sorted map, respectively. Each column also has a timestamp supplied by the client application, but it can be ignored during data modeling. It's used to resolve transaction conflicts. Time to live is used to mark the column deleted after expiration. One level up is a row. It is a set of orderable columns with a unique row key, also called a primary key. What orderable here means is that columns are stored in sorted order by their column names. Different names in columns are possible in different rows. That is why Cassandra is both row-oriented and column-oriented. Physically, a row can't be split to store across two nodes in the cluster, which means the entire row must exist on the same node. Then, column family. It's a container for a set of rows with a given name. The row keys must be unique and are used to order rows. Column family provides great flexibility by allowing different columns in different rows. Any column can be freely added to any column family at any time. Once again, Cassandra is schemaless. The outermost element is key space. It holds a set of column families and contains replication settings of how data is distributed and replicated in the cluster. Though a key space can hold a special structure known as a supercolumn family, it's seldom used anymore. It's rather counterintuitive and confusing for a relational developer to change to Cassandra data model. To master the new data modeling techniques, we need to forget the normalization principles in a relational database. We should focus on the application in addition to the data itself. The application here means how we query the data in the application. Another important consideration is that we need to take into account the physical topology of a Cassandra cluster. A paradigm shift, right? Examples will be given in the later sections to assure our understanding. Cassandra allows collections, set, list, and map as part of the data model. Collections are a complex type that can provide flexibility in querying. We won't go deep into collections in this course. Cassandra doesn't have foreign keys, referential integrity, and hence joins are not allowed. Instead, it encourages and performs best when the data model is denormalized. So, denormalization is normal in Cassandra. The bad practice in a relational database becomes the best practice in Cassandra. Foreign keys and joins can be avoided in Cassandra with proper data modeling tricks. Cassandra doesn't support sequence because of the difficulty of implementing it in a peer-to-peer distributed system. So to have unique values, we use some workarounds, for example, a UUID. Secondary index in Cassandra is not identical to that in a relational database. It can't be created on the primary key itself. Also, it's just to index the data on the local node, and it may not be possible to know immediately the locations of all matched rows without having examined all nodes in the cluster, and so the performance is unpredictable. More information will be provided in the later sections. Cassandra is designed to work in a massive-scale, distributed environment in which ACID compliance is difficult to achieve and replication is a must. ACID means atomicity, consistency, isolation, and durability. While a relational database aims for consistency, Cassandra aims at high availability and eventual consistency instead, because it's governed by the CAP theorem. We must be aware of that in the process of data modeling. In summary, we went through the storage model and the logical building blocks of a Cassandra data model. We also wrapped up this section by highlighting the important differences between Cassandra and other relational databases. Next, we'll go to Section 2 of the course, Design the Data Model. Welcome to the Rapid Cassandra e-learning course, Section 2, Designing the Data Model. In this section, we'll focus on the tools and techniques available for Cassandra data modeling. Cassandra provides a SQL-like language to manipulate its data model, called Cassandra Query Language, and CQL in short. Here, we'll delve into it. We're going to understand what CQL is about. Then the supported native data types will be introduced. It's also good for us to browse Cassandra's source code repository at GitHub. Cassandra introduced CQL in Release 0.8 as a SQL-like alternative to the traditional Thrift RPC API. The latest CQL version is 3.1.7. The syntax of CQL is designed to be very similar to that of SQL. This intent is good for those of you used to writing SQL statements to migrate to Cassandra. It should be noted that CQL 3 is not backward compatible with CQL 2 and differs in many ways. CQL 3 provides a model very similar to SQL. It uses a table instead of a column family to store data in rows of columns. It offers three main types of statements. Data definition statements to set and change how data is stored in Cassandra. Create keyspace, use, alter keyspace, drop keyspace, create table, and so on. Data manipulation statements to create, delete, and modify data. Insert, update, delete, and batch. Query statements, that is, select to look up data. CQL defines a bunch of keywords. It distinguishes between reserved and non-reserved keywords. Reserved keywords cannot be used as an identifier. They are truly reserved for the language. Non-reserved keywords only have a specific meaning in certain context, but can be used as identifier. We may refer to these keywords here, but we won't go through each of them now. Cassandra bundles an interactive terminal called CQLSH for us to write CQL statements. Open a terminal. Type CQLSH. The greeting banner shows the Cassandra instance that is now connected, which is test cluster at the moment. Also, the CQLSH version, Cassandra version, CQL version, and Thrift API version. Suppose we want to create a keyspace called replicas, using the simple strategy replication strategy, and setting replication factor as 1 for a single node Cassandra cluster. We can type create keyspace replicas with replication equals class simple strategy replication factor 1. Then use it. Type use replicas. All right, we created the keyspace. Apart from the CQL statements to implement a data model, we also need different data types to represent the nature of the data we want to put into Cassandra. CQL3 supports many typical data types for columns, as well as the more advanced collection types. The table here gives a quick reference. Most of the time we'll use double, float, int, text, timestamp, time UUID, UUID, and varchar. Interestingly, a special data type called inet is provided to cater for IPv4 and IPv6 IP addresses. As a developer, if we want to find out what these data types are, remember that Cassandra is an open source project. We can go to its GitHub repository to have a peek. The source code is inside the SRC folder. We may go into CQL3. Click on CQL3 type Java. Hey, you see? The native data types are defined here. The Java classes of ASCII type, long type, bytes type, decimal type, and so on are declared in the package org.apache.cassandra.db.marshall. It's worth your time having a glance at it. We've learned the basics of CQL, which offers a SQL-like language to implement a data model and manipulate the data inside. We created a key space using CQLSH. Then we touched on the native data types. We also visited Cassandra's GitHub project to have a peek at the source code of the native data types. In the next video, we'll look into modeling by query. Welcome to the Rapid Cassandra e-learning course, Section 2, Designing the Data Model. In this section, we'll focus on the techniques specific to Cassandra data modeling, called modeling by query. We're going to understand what the modeling by query approach is about. Then, the important considerations on designing a Cassandra data model will be highlighted. Also, the relevant data model design techniques will be covered. Since Cassandra is a non-relational database, the single most important point is that a relational database models data by relationships, whereas Cassandra models data by query. We'll compare the two versions of a simple query between a relational database and a Cassandra data model. Let's start with the relational version first. The diagram here shows a relational data model involving two tables. The stock symbol table is a table storing the master information of a stock, such as the symbol of a stock, the description of the stock, and the exchange that the stock is traded. The stock ticker table stores the prices of open, high, low, close, and the transacted volume of a stock on a trading day. Obviously, the two tables have a relationship based on the symbol column as illustrated by the arrow line. Using SQL statements, they can be defined pretty much similar to what is shown here. Note that a referential integrity constraint is defined on symbol. If we want to know all the day close prices and description of the stocks listed in the NASDAQ exchange on 24th April 2014, we may use the select statement with a join as shown. We may write different SQL queries to return different results, joining different tables together without changing the underlying data model at all. However, in Cassandra, join is not supported. We must use another approach to achieve the same result. How to do that? The answer is to use denormalization. So in Cassandra, we create a table to hold the columns that are required for that particular query. That is, merge the stock symbol table and the stock ticker table together with the required columns as shown. We should be aware of the definition of the primary key. A pair of parentheses for the exchange and tick date columns is added. We'll cover primary key later in the section, and so leave it for the moment. Query is always the starting point of a Cassandra data model, which is just an answer to the query. This is exactly what modeling by query means. Apart from modeling by query, we need to bear in mind a few important points when designing a Cassandra data model. First, data duplication. Denormalization is an evil in a relational data model, but not in Cassandra. It is indeed a good common practice. Cassandra loves commodity-grade hard drives, and hence disk space is cheap. Data duplication as a result of denormalization is by no means a problem anymore. Second, bucketing. A row can hold as many as 2 billion variable columns in a Cassandra node. Even though it seems a large capacity, it is still a hard limit that cannot prevent voluminous data from filling up a node. We may use a workaround technique called bucketing to split the data across multiple nodes. Bucketing requires the client application to generate a bucket ID, often a random number, to break up and distribute the segment of data to different nodes. However, it should not be abused, since it makes read operations consume extra resources to merge and reorder data from various nodes. Valueless column. Column keys can store values, and the not null concept is not applicable to Cassandra, so that column values can store empty values without any problem. Valueless column is a technique to store data in column key while leaving empty value in the column value. It is a common practice with Cassandra. One motivation is the sort by column key feature of Cassandra. But note that space in column key is limited to 64K. Lastly, time series data. They are anything that varies on a temporal basis. For example, processor utilization, sensor data, clickstream of a website, and stock ticker. The stock quote data model is such an example as well. Cassandra is perfect for storing time series data. It is a single layout on disk based on the storage model. Therefore, Cassandra can handle huge volume of time series data in a blazing fast fashion. In the latter sections of this course, we'll develop a complete stock quote technical analysis application in which an explanation of how to handle time series data will be detailed. DataStax has shared a very good article on time series data with Cassandra, highly recommended. We now understand the correct approach to design and build a data model for Cassandra is modeling by query. When applying that approach, a number of techniques can be used to make the data model more effective and efficient. Next, we'll look into indexing. Welcome to the Rapid Cassandra e-learning course, Section 2, Designing the Data Model. In this section, we'll talk about another important element in data modeling, indexing. In Cassandra, it involves both primary key and secondary index that we're going to look at now. We're going to understand the basic and more complicated primary keys of a Cassandra table. Then we'll move on to the secondary indexes. After having such a deep understanding, we can design a high-performance data model. It's meaningless if we can't efficiently look for what we want in a voluminous Cassandra table. Luckily, Cassandra provides very good support on searching and retrieving the desired data by primary key. Cassandra organizes the data in rows. For each row, a row key is assigned so that it can be identified very easily. And we know that a row must reside on a single node. So in other words, the row key determines the node location of the row, and a list of row keys of a table is the primary key. Let's create a table to store the stock quotes in CQLSH. In this example, a basic primary key is defined on the symbol column. It means that symbol is used to partition the rows so that each node stores a data partition of the table and maintains its own primary key. As each node knows the ranges of keys it manages, rows can be located by scanning the row indexes only on the relevant replicas. Hence, it makes the retrieval of rows very efficient. We can use compound primary key to describe a primary key involving more than one column. We may create another table in CQLSH with a compound primary key as shown. Symbol is still used as the row key, or some may say partition key, for finding out the node location. Quote date is used to instruct Cassandra to guarantee the ordering of the rows within the partition. The second part of the primary key is called the clustering key, responsible for ordering the rows in a local node. So the compound primary key sorts the rows of the same symbol by quote date. Now, imagine that Cassandra requires to store stock quotes continuously. The size of the entire row gets bigger and bigger on a node. Cassandra offers a feature called composite partition key to spread the data over multiple nodes. Here you see, we defined a composite partition key with an extra set of parentheses in the primary key clause. The columns exchange and symbol now become the row key. A more detailed explanation of compound primary key and composite partition key with many examples can be found in the DataStax documentation. Cassandra only allows each table to have one primary key, but it also supports multiple secondary indexes on columns other than those in the primary key. The benefit is fast, efficient lookup of data matching a given condition. Basically, Cassandra uses secondary index to find rows not using the row key. The major difference between a primary key and a secondary index is that the primary key is a distributed index used to locate the node storing the row key, and the secondary index is a local index, just to index the data on the local node. Behind the scenes, it's implemented as a separate, hidden, non-distributed table maintained automatically by Cassandra. So it may be unable to know immediately the locations of all matched rows without having examined all nodes in the cluster. This makes the performance of the secondary index very unpredictable. The secondary index is most efficient when using equality predicates, which hopefully limits the set of rows that need to be read into memory. In CQL, we use createIndex statement to create a secondary index. Here, we create a secondary index on the sector column to allow sector to be used in the where predicate. We may also define more than one secondary index on a table, and so we may use multiple conditions in the where predicate to filter the results. In that case, Cassandra selects the least frequent occurrences of a condition to process first for better query efficiency. When a potentially expensive query is attempted, Cassandra requires the allow filtering clause added to the select command. The purpose of the allow filtering clause is to explicitly direct Cassandra to execute the potentially expensive query, despite the performance unpredictability. Secondary index is best on a table with many rows that contain the indexed value. It means the more unique values in a particular column, the more overhead of seeks to query and maintain the index. Hence, it is not for querying a large volume of rows for a small number of results. Well, we ran through the basic primary key, compound primary key, as well as composite partition key. We also covered secondary indexes and understand that they are just a suboptimal way to finding rows. We'll proceed to section 3 of this course, developing an application. We'll roll up our sleeves to write a simple stock quote application called Cassandra Trader. Welcome to the Rapid Cassandra e-learning course, section 3, developing an application. In this section, we'll develop a running real-world application using Cassandra. The application is called Cassandra Trader, which is a simple stock quote application to scan for trading signals. We're going to introduce what Cassandra Trader is about and its conceptual design. Then we'll present how to obtain financial data feed on free internet website, and we'll plan how to actually implement Cassandra Trader. Before we look into the details, here is a disclaimer that Cassandra Trader is only for educational purpose, and we're not assumed to follow such a program to trade financial instruments. Okay, Cassandra Trader serves as a stock screener application to scan for trading signals over the historical data of a stock. As an illustration, we'll use a very simple buying strategy. An alert or trading signal is triggered whenever the close price crosses over its 10-day simple moving average, SMA. So Cassandra Trader should collect and store historical stock quote data from a data feed provider, and then scan and present for trading signals according to our 10-day SMA breakup rule. Not difficult to understand, right? Many free-of-charge data feed providers can be found on the internet. For this course, we'll use Yahoo Finance. It provides historical end-of-day stock quote data, which is sufficient for our use. Open a browser. Type in finance.yahoo.com. Just try Microsoft. Its symbol is MSFT. Click on the Lookup button. Here it is. Click on Historical Prices on the left. Here we may get Microsoft's historical prices. Scroll down to the bottom. Click on Download to Spreadsheet. The historical prices are put into a single file called table.csv. Click on table.csv. It's a CSV file containing the basic stock quote data, date, open price, highest price, lowest price, close price, volume, and the adjusted close price. All right, we have data quote. Let's think about how to develop Cassandra Trader. We'll make it a console application. Of course, the historical data will be stored in a Cassandra database. The programming language is Java, so we'll use Eclipse IDE to manage the project. For Java package dependency environment, we'll use Apache Maven. And we'll use a Java driver for Cassandra from DataStax to access Cassandra objects in the Java programs. Finally, we'll use a well-known open-source library called TALib to help on calculations on technical analysis, such as the 10-day SMA. The project website is ta-lib.org. It supports other programming languages as well. We now know the functions of Cassandra Trader that we're going to build. Moreover, we learned how to obtain historical prices from Yahoo Finance. We also drafted out the implementation approach of developing Cassandra Trader. Next, we'll look into how to set up the development environment and connect Java to Cassandra. Welcome to the second video of Section 3 of Rapid Cassandra. In this video, you'll install and set up the Java development environment on Ubuntu. You'll also write a simple Java program to connect to Cassandra. First, install JDK 7 on Ubuntu. Go to Oracle's website to download JDK. Scroll down a bit. We'll use Java SE 7. Check Accept License Agreement. Click on Linux x64 tar-zip version. Download starts. When finished, switch to the terminal. Change directory to Downloads. Type sudo mkdir/opt/jdk. Extract the tar-zip file by typing the sudo command on the screen. It'll install JDK7 to /opt/jdk directory. Check /opt directory. Alright, JDK is there. Then type the update alternatives commands on the screen. Okay, type java-version. Correct? Type javac-version. Also correct. JDK7 is installed. Switch to browser and open a new tab. Go to Eclipse's download page. Click on Eclipse IDE for Java Developers, Linux 64-bit. Scroll down and click on the preferred mirror site. Download starts. Download finished. Switch back to the terminal. Extract the Eclipse tar-zip file by typing the command on the screen. It'll install Eclipse in the /opt directory. Switch to browser and open another new tab. Go to Apache Maven's download page. Click on Apache Maven 3.2.3 bin tar-zip. Download starts. Finished. Switch back to the terminal. Extract the Maven tar-zip file by typing the command on the screen. Type in vi:/.profile. Go to the bottom of the file. Add the export statements as shown on the screen. Export Java Home. Export Eclipse Home. Export Maven Home and im2. Add Eclipse Home and im2 to the path variable. Save by typing :wq. Source.profile to make it effective. Check Maven version. Type mvn-version. Alright, start Eclipse. Type Eclipse. Click on the OK button to accept the default. Click on the workbench icon. Click on Project. A new project dialog box pops up. Expand the Maven node. Select Maven Project. Click the Next button. Tick Create a Simple Project. Click the Next button. In Group ID text box, type com.rapidcassandra. In Artifact ID text box, type Chapter 0301. Then click the Finish button. A project called Chapter 0301 is now in the Package Explorer on the left-hand side. Expand Chapter 0301. Select pom.xml and right-click. Select Maven near the bottom of the menu. Select Add Dependency. In Group ID text box, type com.datastax.cassandra. In Artifact ID text box, type Cassandra-driver-core. In the Version text box, type 2.0.1. Click OK. Select source/main/java and right-click. Select New, Class. In Package text box, type Chapter 03. In Name text box, type Chapter 0301. Tick Public Static Void Main checkbox, then click Finish. Chapter 0301.java shows up in the editor. To save typing time, copy the code in the completed Chapter 0301.java in the accompanied source directory. Click on the Save button, then click on the Run button. In the console window, you see the Java program connected to Cassandra and showed the name of the cluster and its node information. In summary, we downloaded and installed the development software, namely JDK7, Eclipse, and Maven on Ubuntu. We also configured the shell to run the development environment. Then we got Cassandra Java driver in Maven repository through the Eclipse IDE. Finally, we wrote a very simple Java program to connect to Cassandra and collect its metadata information. Next, we'll conduct the design of Cassandra Trader. Welcome to the third video of Section 3 of Rapid Cassandra. In this video, we'll conduct the design of Cassandra Trader before actually writing the code. We'll start from the data model of the Cassandra database. Then we'll apply the model by query techniques to design the tables. Then we'll design the various Java classes to be coded in the next video. First, we create a keyspace, called packed CDMA, with the replication settings for a single node cluster. Switch to the terminal. Type in CQLSH, type in the create keyspace statement as shown. OK, we'll create a table called quote to store the historical prices collected from Yahoo Finance. Among the data of the historical prices, we'll store price time as date, open price as open, high price as high, low price as low, close price as close, volume as volume, and add a column symbol to differentiate the stock that the quote belongs to. Note that we drop off adjusted close here. The primary key is simply symbol and price time. This way, all historical prices of a stock will be stored together in a node. Switch back to CQLSH. Use packed CDMA keyspace. Create the table quote as shown. Alright, it's time for us to think about how Cassandra Trader will interact with the Cassandra database. Obviously, we'll insert or update the quote table using the insert statement as shown. Also, we'll select historical data of a stock in a date range using the select statement. The primary key of the quote table naturally fits for that, and so no need to denormalize. Also, we don't want to repeatedly download the historical prices that are already stored. To check that, we'll have a query to get the latest date of a stock in the quote table. Now we can discuss the Java classes of the Cassandra Trader application. First, the main class is of course Cassandra Trader, which controls the major processing flow. Then we need to programmatically collect historical prices from Yahoo Finance. Yahoo Fetcher class does exactly that. To ease the manipulation of the historical prices, we'll create an entity Pojo class quote as their representation in runtime. We'll also encapsulate the details of managing a Cassandra connection inside Cassandra Manager class. Similarly, we'll wrap up the data access logics in Cassandra Trader DAO class. The core logic for scanning trading signals using TA-lib will be put into Trading Signal class. Lastly, Cassandra Trader Util class will provide handy conversion functions for strings. We've followed the modeling by query techniques to design the data model and create the keyspace and the table for Cassandra Trader. Then we touched on the Java classes which make up Cassandra Trader and described their brief responsibilities. In the next video, we'll write Java code in the Eclipse IDE to bring Cassandra Trader to life. Welcome to the fourth video of Section 3 of Rapid Cassandra. In this video, we're going to start writing the code. We'll create the Java project and set up the dependency in Maven and walk through the source code of the Java classes. Following the similar procedure in Section 3.2, connect Java to Cassandra, so we can create another project called Chapter 0302. It contains 4 packages to group the Java classes into more manageable pieces. Cassandra Trader is in com.rapidcassandra.chapter03 package. Quote is in the model package. Cassandra Manager, Cassandra Trader DAO, and Trading Signal are in the repository package. Cassandra Trader Util and Yahoo Fetcher are in the Util package. The source code structure is not clumsy, right? Then we need to add dependency packages. Double-click pom.xml. Click on the Dependency tab. We add javax.persistence for the quote Pojo class, Cassandra-driver-core for Java connection to Cassandra, and TA-lib for the technical analysis library. We may have a brief look at the Java classes. First, Cassandra Trader. The getData function handles the collection of historical prices of a stock and storing them into Cassandra. It checks the latest date of the historical prices of the stock and adjusts the start date of collection to avoid wasting resources. The data feed is obtained by calling the getStock function of Yahoo Fetcher class. The data is stored in a buffered reader, which will be looped through to convert to a quote object. The quote object will then be persisted in the quote table in Cassandra. Another function, scanTradingSignal, as its name describes, retrieves the historical prices of a stock from Cassandra, and then calls the SMA10 breakup function of TradingSignal class to generate the trading signals. The main function simply specifies the symbol of the stock and instantiates Cassandra Trader DAO and Cassandra Trader. The date range of the scanning can be given as the FromDate and ToDate variables. Quote class is simply a POJO imitating a row in the quote table for Java runtime manipulation. Nothing special here. Next, Cassandra Manager. It's also a simple class for the management of Cassandra connection. The connect function will connect to a Cassandra cluster specified by node, port, and keyspace parameters. The close function simply disconnects from Cassandra. Cassandra Trader DAO includes all data access logics and requires a bit of explanation. It instantiates Cassandra Manager, and the CQL statements we discussed before are coded here. The constructor connects to the Cassandra keyspace and prepares the CQL statements. The function saveQuote uses the prepared insert CQL to persist a quote object into the quote table. The selectQuote by symbol and date range function calls the prepared selectCQL to retrieve historical prices from Cassandra and populates them into a list of quote objects. The lastQuoteDate by symbol function calls the prepared selectCQL to get the latest date of the historical prices of the given stock. Then TradingSignal class. A TALib instance is created in the constructor. The SMA10 breakup function accepts a list of quote object which represents the historical prices to be scanned. To call TALib, we need to convert the close prices into an array of doubles. Also, TALib will output its computation results to another array of doubles. We call the SMA function of TALib to calculate the 10-day SMA and scan for the crossover trading signals. When found, simply print the details of the signal on the console. Cassandra Trader Util class is just a library for conversions between string to date and decimal values. Yahoo Fetcher class handles the system interface to Yahoo Finance. The getStock function collects the historical prices, in which the URL is the web service API, and we store the data stream in a buffered reader. The parseQuote function extracts the details of the data fed into a quote object. In summary, we created the Cassandra Trader project in Eclipse IDE and went through the source code structure. We also briefly browsed through the Java classes and explained the core functions. Next, we'll test drive Cassandra Trader with live data and verify the trading signals. Welcome to the last video of Section 3 of Rapid Cassandra. In this video, we'll test run Cassandra Trader that was developed in the last video. We're going to put Cassandra Trader on the road to test with live data, verify the database, and validate the trading signals generated. Let's switch to CQLSH to check the quote table first. Type in select asterisk from quote. No record is returned. That's correct. The table is new and empty. Go back to the Eclipse IDE. Double-click Cassandra Trader on the left. In Cassandra Trader, we're going to collect historical prices of Citigroup, whose symbol is a big letter C. Change the to date to 14th November 2014. Right-click, select Run As, and then 1 Java Application. Look at the console at the bottom. We see that the URL of the web service call to Yahoo Finance is shown. Okay, 3 trading signals are found. Before checking them, let's check the Cassandra database first. Switch back to CQLSH. Run the same query again. This time, more than 3,700 rows are returned. And the last row shows the price time is the same as to date. We type in select star from quote limit 1. It returns the row of the earliest historical prices. It is the 3rd of January, year 2000. Okay, the Cassandra database is correct. We now turn to validating the trading signals. Open the Chrome browser. Input C in the input box for symbol and click on the Go button. Select Interactive on the left menu. A line chart of Citigroup is shown. Scroll down a bit, click on 3M to zoom into the portion of the latest 3 months. Then click on the Chart Type button, select Candle. Then click on Indicator, Click on the pencil icon of Simple Moving Average and enter 10. Click on the chart to close the indicator dialog box. We now have a candlestick chart of Citigroup for the latest 3 months with a 10-day SMA superimposed on it. Let's check the trading signals one by one. Start from the rightmost portion of the chart. The signal happened on the 21st of October because the close price of the previous day was under 10-day SMA, but on that day, the close price was above the SMA line. So Cassandra Trader produced this trading signal correctly. Let's move on to the next one. In mid-October, we see that there was a signal happened on the 14th of October, which is also found by Cassandra Trader. Finally, at the beginning of October, the third signal happened on the 8th of October. It's also discovered by Cassandra Trader. There are other signals in the period since the 1st of July, and they are left as your exercise. So this eyeball check validated that Cassandra Trader works like a charm. All in all, we tested Cassandra Trader with live data, although we only used the historical prices of Citigroup. It's indeed very easy to be modified to multiple stocks. We also verified that the historical prices were successfully saved into the quote table in Cassandra. Finally, we eyeball validated the trading signals produced by Cassandra Trader with a technical analysis chart provided by Yahoo Finance. Now we have Cassandra Trader working in the development environment. In the section, we'll consider the many aspects of deploying Cassandra Trader into a production environment. For example, a 2-node cluster, replication strategies, and so on. Welcome to the Rapid Cassandra e-learning course, Section 4, Deploying to Production. In this section, we'll expand the single-node cluster done in the last section to a multi-node production cluster. The first thing to consider when migrating a development cluster to a production one is replication strategy. We're going to choose the appropriate replication strategy for Cassandra Trader. Then we'll actually expand the cluster with the planned settings, as well as migrate the data to the cluster. And we'll modify Cassandra Trader source code to connect to the cluster. Cassandra provides 2 replication strategies for different needs. Simple strategy is suitable for a cluster in one and only one data center, so it's not really expandable. Another more common choice is network topology strategy, which is highly recommended for any future expansion to a multi-data center cluster. Obviously, we choose it for Cassandra Trader. We'll migrate to a bare minimum 2-node cluster as illustrated in the design diagram here. The cluster name will remain test cluster, and both nodes will be in the same rack, rack 1, in the same data center, NY1. We'll need to modify 2 Cassandra configuration files to make it real. First, cassandra.yaml. UBTC01 is the seed node. Listen address is set to empty, and RPC address 0.0.0.0. And endpoint snitch is gossiping property file snitch. We also changed the name of the data center and the rack to NY1 and rack1 respectively in Cassandra rackdc.properties file. As we've stored historical prices of some stocks in the single node cluster and don't want to download them once again, we'll follow the steps shown here to migrate the data. All right, here we go. First, switch to the Java development environment, stop Cassandra. Make a temp folder in home directory. Copy all SS tables of packed CDMA keyspace to a temporary location just created. Start Cassandra again. Assuming we know how to install a new Cassandra node and configure the network, we'll skip the steps in this video. Then apply the changes in the configuration files to both nodes. Start the seed node first, and then the other node. We'll then use CQLSH to create keyspace packed CDMA with new replication strategy setting and create table quote. Switch to the Java development environment. Finally, we load the backup SS tables back to the cluster using SS Table Loader. Open CQLSH and select all historical prices from quote to validate the migration. All historical prices survived. We then proceed to modify the Cassandra Trader source code to connect to this cluster. First, we add a new method connectCluster in Cassandra Manager class to connect to multiple nodes. Then, we change the constructor of Cassandra Trader DAO class to connect2call connectCluster method instead. Finally, go back to Cassandra Trader. we change to call the cluster version of Cassandra Trader DAO class constructor. Set the symbol to a new one, say ORCL. Run again. Alright, it finished successfully. Let's validate the result in CQLSH. Select all historical prices of ORCL. Perfect. Everything works like a charm. We now know the steps of scaling out a single node cluster to a production one, and choose the right replication strategy. Moreover, we learned how to migrate existing data to the production cluster. We also modified Cassandra Trader to work with the production cluster. Next, we'll look into how to configure and test a resilient cluster, which is very important in a production system. Welcome to the second video of Section 4 of Rapid Cassandra. In this video, we'll look at making a resilient Cassandra cluster. We'll learn about how to configure a resilient cluster by data replication. Then, we'll simulate a node failure scenario to test the effectiveness of the resilient cluster. We'll also restore the failed node afterwards. Now let's change the replication setting of the key space. Open CQLSH. Type in DESC keyspace
packed CDMA.
We see that its replication setting NY1 is equal to 1, meaning that no replica is created in the data center NY1. Let's change it. Type in alter keyspace
packed CDMA
with replication equals brackets class network topology strategy, comma NY1 2 close brackets. The effect is to have UBTC02 become the replica of UBTC01 and vice versa. Exit CQLSH. Run node tool status. The load is not balanced between the two nodes. We need to run node tool rebuild on each node to make the key space setting effective. Node tool status again. Now the load is more or less balanced. We may simulate a node failure on UBTC02 by shutting down its network. Node tool status showing that UBTC02 is down. We now turn to Cassandra Trader. Change the symbol to JNJ and run the app. It still works, even though one of the nodes is failed, and we haven't changed any code in connecting to Cassandra. Back to the terminal and node tool status. We now try to bring up the failed node again. Check the status. All nodes are up and the load on both nodes is increased, which should be caused by data replication and hinted handoff repair mechanism. To verify this, open CQLSH. Type in select * from
packed CDMA
.quote where symbol equals J&J. All the J&J's historical prices are here. Test Cassandra Trader again. This time we're interested in INTC. The app runs perfectly. Hence, the failure and restoration of a node in the cluster don't interfere with the running application, provided we've configured the replication settings in the key space. It's also worth mentioning that we don't need to change a single line of source code in catering for the failures of the cluster. It's totally transparent to the app. We've set up a Cassandra with resilience and simulated a node failure. We've seen that the client application was not affected by that failure and proved the cluster highly available. Then we restored the failed node, which was also transparent to the client application. In the next video, we'll touch on monitoring and tuning of Cassandra. Welcome to the third video of Section 4 of Rapid Cassandra. In this video, we'll look at the monitoring tools provided by Cassandra and some of the basic performance tuning tips. We'll learn about the most typical options of Node Tool to perform day-to-day monitoring of a cluster. Then we'll have a look at the log structure, which contains pertinent information for troubleshooting. We'll also highlight some important performance metrics and their improvement methods. First, Node Tool. We've been very familiar with the status option. It's used to provide information about the cluster, such as the state, load, and IDs. It gives a very concise summary of the cluster. Actually, Node Tool is not just that. We may use some other options, for example, NetStats. It gives network information for a node, focusing on read-repair operations. The Info option also gives valuable node information, including token, on-disk load, uptime, Java heap memory usage, key cache, and row cache. The TP Stats option provides statistics about a number of active, pending, and completed tasks for each stage of Cassandra operations by thread pool. A high number of pending tasks for any pool can indicate performance problems. For a particular table, we may use the CF-stats option to get statistics about one or more tables. We use dot notation to specify one or more keyspace and table names, such as nodetool CF-stats
packed CDMA.
.quote. It presents the read and write counts and latencies, metrics about SS table, mem table, bloom filter, compaction, and so on. These are the most commonly used options of nodetool for day-to-day monitoring. Another important source of monitoring information is the system log of Cassandra. Beware that the system log is for the local node only, which means we need to go into each and every node to investigate the logs when necessary. As shown here, we found that hinted handoff was executed while we were restoring the failed node in the last video. Based on the information given by the monitoring tools and system log, we may discover opportunities for performance tuning. The first thing we usually watch is the Java heap memory. Java virtual machine configuration settings are controlled in the environment settings for Cassandra, cassandra-env.sh. Basically, it already has the boilerplate options with brief explanation. For example, the options for tuning garbage collection. Another area we should pay attention to is caching. Nodetool info really helps in this case. The important metrics of key cache and row cache are shown in the last two lines. In the event of high memory consumption, we may consider tuning data caches. Indeed, performance tuning is a large and complex topic that itself can be a whole course. We've just scratched the surface of it. We've grasped the nodetool and understand the structure of the logs produced by Cassandra at runtime. Then we presented some basic but important performance metrics and their tuning opportunities. In the next video, we'll look at evolving the data model in the production cluster. Welcome to the fourth video of Section 4 of Rapid Cassandra. In this video, we'll implement a change on the Cassandra Trader data model. We'll learn about how to change an existing data model. Then we'll modify the source code of Cassandra Trader to work with the change and execute a test run afterwards. At present, Cassandra Trader extensively uses symbols to differentiate different stocks. However, it's quite difficult to memorize each stock symbol. Instead, it's easier for us to internalize the stock name, and so we need to add a column symbol name into the quote table. We'll execute the alter table statement to add the column on a node. Cassandra then automatically synchronizes this data model change to the remaining node. To capture the stock name, we still make use of Yahoo Finance. As shown here, ORCL is actually Oracle Corporation, so we'll scrap the stock name on this webpage. But first, we alter the quote table in CQLSH. Open CQLSH. Type in alter table
packed CDMA.
.quote, add symbol name varchar. Double check again. All right. Go back to the Cassandra Trader source code. Obviously, we need to reflect the additional column in the Pojo class quote. Then Cassandra Trader DAO class. We'll make several modifications for the new column symbol name. We modify the insert statement, and accordingly we change the save quote method. Further, we change the select quote by symbol and date range method. That's all for symbol name. We also need a way to scrap the stock name from Yahoo Finance. So we add a new method, getStockName, in Yahoo Fetcher class. It uses an open source library, JSoup, to traverse the collected web page and extract the text element on the page. JSoup is basically an HTML parser for Java. We can make it available to the Cassandra Trader project by adding the dependency properties in Maven, as shown on the screen. Now, test run Cassandra Trader. This time we use GOOG. OK, switch to CQLSH. Type in select asterisk from
packed CDMA.
.quote, where symbol equals GOOG. Now the stock name is saved in the quote table. We've altered the table definition for a new column symbol name. Cassandra propagated this data model change to all nodes in the cluster. We then modified the source code to accommodate the new column, and used JSoup to parse the HTML page and extract the stock name automatically. Finally, we test and validate the enhanced Cassandra Trader. Next, I'm going to summarize the course. Welcome to the last video of Section 4 of Rapid Cassandra. In this video, we'll sum up what we have learned in this short course. We'll recap our journey beginning from Section 1 till the end. We'll also explore the areas of Cassandra Trader for those of you who want to further enhance it. Lastly, we'll be introduced to some useful resources to finish this course. Our journey started in Section 1, covering Cassandra's high-level architecture, some of its pertinent concepts, and the unique features that it provides. In Section 2, we delved into the nuts and bolts of data modeling in Cassandra. We introduced the latest version of CQL, the native data types, the modeling by query techniques, and indexing. Then, in Section 3, we rolled up our sleeves to design, build, and test a simple yet comprehensive Java application, Cassandra Trader. Many techniques of interfacing with Yahoo Finance were illustrated with real examples. Then, in Section 4, we further extend Cassandra Trader to the production deployment. We scaled out the development cluster into a multi-node cluster with explanation of replication strategies and legacy data migration method. We also covered resilience and high availability, the tools for monitoring and tuning, and demonstrated implementing a change request on the data model and the subsequent modifications in the Cassandra Trader source code. I think the contents are adequate for a developer to start building Java applications with Cassandra. If you're interested in further enhancing Cassandra Trader to help you scan stocks, here are some areas worth mentioning. As Cassandra Trader is a console application, it may be modified to accept command line arguments, rather than hard-coding the symbol inside the main method. Or, you may create a watch list of the stocks in a Cassandra table and modify the program to loop through it, so that a large number of stocks can be scanned automatically. If you want to use technical analysis techniques other than simple moving average, you really need to look into TALib in detail. It provides a bunch of different technical analysis indicators such that you may modify trading signal class to try them all. In case you want to have a detailed documentation of Cassandra, I strongly recommend you visit DataStax.com. It always aligns the documentation with the latest release of Cassandra. Also, it provides Cassandra driver for various programming languages. If you want to learn more about use cases, Planet Cassandra is definitely the choice. You may also socialize with Cassandra lovers all over the world. Another useful source is Internet Relay Chat. Many Cassandra users and developers in #Cassandra channel on Freenode server. I've really enjoyed creating this course for you, and I sincerely hope that it's as useful for you as it has been fun for me. Your comments are always welcomed, and you may contact me through Pact Publishing. Thank you for watching.